dissolved this table sugar earlier, the sucrose. It just dissolved. But when I dissolved this table salt, sodium chloride, it dissolved and dissociated. That means I get more particles out than I put in. Pretty awesome, right? Kind of like if you open up a Rolos tube and the Rolos spill out. You get more pieces of candy in than you might think just looking at that one Rolo. But if you were to open up a Kit Kat bar, the bars stay together. That's kind of like sucrose. It doesn't dissociate, it just dissolves. So when something dissolves, it gets a full coat of water. But when something dissociates, it actually breaks up into its like component ions, so charged particles. So if you look at sucrose, it looks like it's got two things. It's made up of a glucose and a fructose stuck together. But they're stuck together through strong bonds, through covalent bonds. Those bonds don't just come apart when you dissolve something. When you dissolve something, all you're doing is you're giving it a coat of water. Because these are held together tightly and with those covalent bonds, like the kinds of bonds that are holding together the individual fructose and the individual glucose, the same type of bond is holding together those two subunits. They just happen to have come from two subunits glued together. But in the case of sodium chloride, those are just held together by charge attractions. You have a positively charged sodium ion and a negatively charged chloride ion. So they like to hang out together. But when you give them water, the water likes to hang out with those two, and so the ions dissociate. We call compounds that, or molecules, or not molecules, we call compounds that dissociate like this electrolytes. And they conduct electricity because electricity is the flow of charge, and when you have these charged molecules, well, now another charge comes by, they can go move towards that charge and that sort of thing. And so electrolyte solutions are able to conduct electricity. When it comes into play in the lab is often when we're calculating molarity. We're calculating based on the formula unit, based on the molecular weight for the unit. So it's like for a roller bar, but then when you open the roller bar, you get more pieces of candy. So I put in 5 moles worth of sodium chloride, and I get 5 moles of sodium and 5 moles of chloride. So what is a mole? Well, a mole is like a biochemist dozen. A mole is like a dozen, except that instead of 12, it's 6.02 times 10 to the 23rd copies of something. And if you were to order a mole's worth of bagels, you would basically have enough for 86 trillion bagels per person, which is a lot of bagels. But when we're talking about really, really tiny molecules, you're able to stuff those in. So I'm able to fit 5 moles worth of sodium chloride into 1 liter to give me a 5 molar solution, which, by the way, is really handy in the lab. When we're calculating molarity, we're calculating based on the formula unit, based on the molecular weight for the unit. So it's like for a roller bar, but then when you open the roller bar, you get more pieces of candy. Going back to our bagel example, it's kind of like those bagels were sliced. And so when you open up the box of bagels and you go to distribute them, well, now you have twice as many bagels. So if you ordered a dozen bagels, well, now you have 24, so you have like 2 dozen pieces of bagel that you could hand out. Same sort of thing, except here we're dealing with ions. Might make you happier, and or have some sort of effect, maybe making you happier. And in biochemistry, some sort of effect can be things that have to do with colligative properties, such as changing the boiling point, the freezing point, the osmolarity, things like this. So it can be important to know how many particles something's going to break into when you stick it into liquid. And to help us calculate based on this, we have to apply something called the Van Hoff factor. So because sodium chloride breaks up into 2 parts, it has a Van Hoff factor with this I of 2. And so we can multiply the molarity of the unit by the Van Hoff factor to get the number of particles, and then we can take that into consideration when we're calculating things. Complicating note that actually the Van Hoff factor, that's like optimal, like if the ions were just like totally separate from one another. But what happens is they still like each other, so sometimes they kind of like, you get this like ion pairing where they actually like stick together. So it's kind of like some of the Rolos in the tube, kind of like maybe they melted or something and they stuck together a little. So this is going to decrease the number of actual like particles that you have, like theoretically wise, I mean in terms of their effects on the colligative properties, because those ions are still kind of hanging out. When you look at the bottle for some sort of compound, you'll see like FW or MW, this is, or MM or something. So this is FW, stands for formula weight. And so it's telling you how much a mole's worth of the formula unit is. So the formula unit is like what you're buying. So you're buying the sodium chloride. You're buying that roller bar, even though the roller bar has individual pieces in it. When you look at the wrapper, it's going to tell you how much it weighs in terms of the whole bar thingamabob. And so similarly, the sodium chloride, this formula weight is telling you that a mole's worth of sodium chloride is going to weigh 58.44 grams. And some of that is going to come from the sodium, and some of it's going to come to the chloride, but if you weigh out that much, you're going to get 1 mole's worth of each of the sodium and the chloride. When it comes to the sucrose, here you see that the molecular weight is 342.3. So here, MW stands for molecular weight. Sometimes you see molecular weight and formula weight used interchangeably, but technically a molecule is something that's held together only by covalent bonds. So it wouldn't be correct to say formula weight or molecular weight for sodium chloride, because sodium chloride, well, that's not a covalent compound, and so it's not a molecule. It's like kind of two molecules that are stuck together, where they're just hanging out. They're not really permanently stuck like you have in this case of sucrose. So when you go and calculate out, okay, the molecular weight, 342.3, this means if I wanted a 1 molar sucrose solution, I would need to weigh out 342.3 grams of sucrose. But I would get that same amount. I would get 1 molar worth of sucrose, whereas if I were to weigh out 58.44 grams of sodium chloride, I would get a mole's worth of sodium and a mole's worth of 1 molarity of sodium and 1 molar molarity, a concentration of 1 molar for the sodium and a concentration of 1 molar for the chloride. And that's going to come into play when it comes to colligative properties. And this is one of the reasons why salts are really good if you want to increase the like colligative action of something. One of those colligative properties, if you want a lot of particles, salts are going to give you more particles for what you put in than if you were to put in something like sucrose. And so this makes it better to salt your streets with sodium chloride than to salt them with sugar. Although salt's not that great for the environment anyway.